Okay, off we go. So, last time we finished up, chapter 6. Moving on now to chapter 7. Chapter 6 was just broad strokes, let's not oversimplify, but basically it was about vector calculus in 2 dimensions. Right? So, the big theorem that we saw was Green's theorem. Green's theorem is exclusive to 2 dimensions. It's about a 2-dimensional region in the plane and its boundary curve. Now we had to do some other things. We had to define, what is a vector line integral. We had to set up some parameters. We had to talk about accumulating quantities and, set up a framework, right? But the big theorem was Green's theorem, 2 dimensions only. Chapter 7 is basically the same thing in 3 dimensions. Pretty much. Again, broad strokes, oversimplifying, and it's not as simple as it was in 2 dimensions. It gets a little bit weirder, but it also gets a little bit more relevant. Chapter 6 is a great segue into chapter 7. We live in a 3-dimensional world. That's really what we need to understand most. And yet having that 2-dimensional segue is going to be very helpful. Okay, here we go. So the first thing we're going to need to do is talk about parameterizations. After all, again, we can't state Green's theorem without vector line integrals, and you can't define vector line integrals really without parameterizations. That's how we write down the formula for it. So we're going to need to figure out how to parameterize now surfaces. Right? So this is our big first thing, how to define a parametric surface. Good news. It's a lot like what we've done already. It's position as a function of now 2 parameters instead of just 1. So a parametric curve gave position as a function of time. Time is a convenient sort of point of view. Really, a parametric curve is position as a function of 1 parameter. And it's nice that we can think of it as time. But position as a function of 1 parameter. Now, position as a function of 2 parameters. Now, good news, we've already seen an example of this. This exact function right here came up in section 1.5. This is what we call a parameterization of a plane. Now, I'm just going to scroll back here. I had this already prepared, of course. This is from the lecture notes of section 1.5, right? This goes way back. And you see we talked about how to parameterize a plane, and we wrote down this formula, right? And the big idea, again, we talked about previously, was you take some starting point, and then you have 2 direction vectors, v and w, and exactly which multiples of those we need to add to that original dark blue point to get to whatever final point in the plane we might be interested in is decided by these 2 parameters. Wrong color. These 2 parameters, s and t, that basically tell you, loosely speaking, how far to go in those directions, v and w. Right? So there's your 2 parameters, is s and t. Okay, alright, so here's just the exact same thing, just kind of saying it over again, reminding you, and using it as our first example, reminding you of it as our first example of a parametric surface. Okay, so by the way, take time as needed if you need to go back and remind yourself of what the deal was back in section 1.5. Now is a good time, of course. This is where we stopped in section 1.5, and we went on to other things. We're going to now continue with more parameterizations of surfaces. Okay, all right. So, you know what? I always get ahead of myself on this. These 2 parameters, we are going to lose something in the fact that there are 2 of them. As when we talked about parametric curves, it was very handy to think of the parameter as being time, right? And again, it rolls off the tongue so nicely to say position is a function of time. Right? So now that we have 2 parameters, I can't visualize them both as being time, right? That'd be pretty weird. I guess maybe, I've toyed with the idea that maybe there could be like the coolest sci-fi movie ever where there are two separate times. Right? I think it'd be kind of wild, people moving around in two-dimensional time. Anyway, but basically it's not a practical metaphor. So, too bad, but time is not an essential point of view on a parameterization, so it's a small sacrifice. Okay, moving along. How do we create parameterizations? Right? We got this great idea we can parameterize surfaces just like we can parameterize curves. Basically, just two parameters instead of one. How do you make these parameterizations? I'm going to start with my favorite. My favorite is the graph parameterization. Rings a bell, I hope, right? That was one of our big tools when we first started talking about parametric curves, was the graph parameterization of a curve in 2 dimensions. Now we're going to talk about the graph parameterization of a surface in 3 dimensions. And let's take a quick moment to recognize what we have there in purple. That's an equation involving 3 variables. That is something in 3 dimensions. It gives you a value of z for every point in the 2-dimensional xy plane that is, kind of part of R3. And so it gives you a 2-dimensional surface. So this is a surface in 3-dimensional space. It is a graph, and the big trick, the thing that makes it work, my favorite parameterization tool of surfaces is just like it is for curves. Whatever the input variables are, let those be your parameters. Same rule. Whatever are your input variables, make those your parameters. And you'll notice that's the very first thing I write down in the parameterization. Oh, missed. Sorry, spaced. There we go. Input variables are the parameters. What else? How am I going to find my formula for z? Well, I don't even get to decide anymore what my formula is going to be for z because it's a graph, because z is a function of the inputs, and because the inputs are the parameters, the formula for z is automatic. You just take your new expression for x and y, in this case, as s and t, plug that into your equation, and out comes what z is. Boom, poof, parameterization. Position as a function of 2 parameters. Okay. How we doing? Is everybody on board? Questions? Okay. Here's another example. By the way, there's nothing magic about alphabetical order. It doesn't have to be x and y that are the input variables. You take a situation like this one here. We have an equation, and I can't solve for z. Practically speaking, anyway. Okay, well, are we dead in the water? No, because I can solve for y. No problem. You solve for y. Now I have a graph in a, kind of a sideways sense of the word, right? But I have one of the variables solved for in terms of the other 2. So my input variables now being x and z, I let my parameters be my input variables. There you go. X and z are my input variables. And again, there's kind of nothing left for me to choose. Y now has to be that. And again, we win. Position x, y, z is a function of 2 parameters. Same story, just different shuffling of which variables are playing which roles. Okay, what do you think? Everybody happy? Okay. All right. By the way, there's another version of this, another sort of twist. It doesn't even have to be rectangular coordinates. Right? Any coordinate system. As long as you can solve for one of the coordinates in terms of the others for that coordinate system, of course. Right? Pick any coordinate system you like. If you can solve for any coordinate in terms of the others, and that's kind of what a graph is, if you think about it, then it still kind of works. You just have to start with your coordinate conversion formulas. Right? So when you talk about a parameterization, typically when people say a parameterization, what they mean is not just position as a function of parameters, but rectangular position as a function of parameters. And so you do have to plug into the coordinate system. But again, no big deal as to how to do this. If you have, for example, this equation right here, well, it's a graph. I have rho solved for. Rho is a function of phi and theta. Now let me address a little micro point. A lot of students get upset about the following. You look at that formula, like, where I don't see any thetas. Where's the theta? How is rho a function of theta? And the answer is, it's an awesome function of theta. It's a function that doesn't even depend on theta, right? As far as theta is concerned, this is effectively a constant. So it's still a function, right? And I'll remind you, let's go back to singularity calculus, just a quick second, quick little mental exercise. If I have y equals f of x, and if y equals f of x is 4, still a function of x. It's just an easy function of x. So this is good news, not bad news, that there's no thetas in there. No problem at all. And notice, I just plug in everywhere I see a rho, I put cosine theta. Just, again, follow it. I don't even have a choice in the matter. That's the deal with graph parameterization. Whatever your formula is for the one variable you solve for in terms of the others, plug it in there. There you go. And again, position is a function of two parameters. Now the good news here, a little bit of a tweak, a little bit of a twist. You'll notice I did not rewrite in terms of S and T. And the point is I don't have to. In a case like this, if I had left x as x, and not rewritten it as S. Right? And likewise, if I had left Z as Z and not rewritten it as T, then notice I would have X and Z playing two different roles. X and Z in this scenario would be both input and output variables, and that leads for the potential of confusion of variables. And it's there's a highly undesirable scenario. So that's why we make up new variables, S and T. But notice, I don't have to here. If I just leave phi and theta, right, there's no reason to rename them as S and T. No confusion of variables. Phi and theta are my inputs. X, Y, and Z are my outputs. Not only does this not have a confusion of variables problems, I get to retain the geometric significance and therefore my mental convenience of what those parameters represent geometrically, and that's a good thing, right? So no reason to rewrite in terms of S and T in a case like this. Okay, is everybody happy? Okay, all right. Okay, this next one, this is optional. I used to spend time covering this, and it takes time, and it is a kind of a cool trick. It's a neat thing to be aware of, but when it comes to surfaces, it's not very often that this ends up being super useful. So you'll notice I've made it optional now. You don't have to look at this, but I do think it's a pretty cool idea. And I'm going to hit some very broad strokes. If you do choose to go through this, then notice all I've done is I've taken a graph and I've described points on the graph by using the graph parameterization. That's the first part. No, that's no big deal. Next, I have rewritten the graph as a level set and done some algebra. And this idea of representing moving by a distance 1 perpendicular to the original green surface, I can find that unit normal vector that does that by, again, that orange algebra there. And again, this is optional. Look through it if you'd like. I think it's a pretty straight read. We just use the fact that gradients are always perpendicular. That's what I'm looking for. Perpendicular to level sets. That's why I rewrote it as a level set instead of a graph. But anyway, once you have that observation made, you just notice that per the picture, green plus orange gets me to points on the surface I'm interested in. Right? That's the H surface that I'm interested in there. Right? It's just green plus orange. So this idea of using vector algebra, vector addition, to turn the hard problem of that purple surface into a couple of relatively easy problems, green and orange, again, pretty cool technique. Not that different from the bicycle tire example that we did back in, whenever that was, or chapter, I think it was somewhere in chapter 1, where we understood that the axle of the tire actually has a really simple formula, and the spokes have a pretty simple description in terms of time, and then so you, again, turn hard into easy. So anyway, if you're interested in this, give it a look. It's not required. Okay, this next technique, very useful. Oh, I should interject. A lot of what I'm doing here with how to create parameterizations is not in the book. I think that's, I'm going to call it an unfortunate oversight. What the book does is it gives you several examples of parameterizations where they start with the parameterization given. My experience, I had to parameterize a lot of surfaces over my many physics courses that I took, and y'all will probably be doing similarly in your engineering courses here and there. My experience is that parameterizations usually don't come as given in life. Right? Most of the time that I needed to use parameterizations, the surface was described some other way, and I had to create the parameterization. Right? So that's why I'm focused here on how to create parameterizations. Feel like I'm filling in a gap that the book kind of gloss over. And for whatever it's worth, a lot of multivariable calculus textbooks gloss over this. I think it's weird. I don't know why. Okay. Anyway, back into it. Here is an interesting little geometric challenge. How would I parameterize the torus? Right? Sort of the surface of a donut. The surface, a three-dimensional world, a two-dimensional surface in a three-dimensional world. We're going to need to parameterize such things, and how would I parameterize this surface? It's not a graph. I can't use the graph parameterization. It's not a plane. What other tools do we have? So here's my answer to that question. I like to think of this as creating a coordinate system. So let's speculate on the following question. Suppose that I wanted to be able to describe points, right, on the surface of the surface of the donut, and it was on the torus. I want to describe them in the most convenient way possible. Right? I could write down three coordinates. I could write down X, Y, Z. But that's, first of all, that's three coordinates. Why should I need to write down three coordinates? I can totally do it in two. But more to the point, no pun intended, the idea of using three coordinates, it'd be very difficult to tell at a glance whether the point that you've written down with X, Y, Z is even on the torus. That's a non-trivial question. How would you know if that's even a point on the torus? So this idea of having a coordinate system that makes sense on the torus would be a very handy way to do business on the surface of the torus. So here's what I would do if I had some point like so. And I wanted to describe to you where that point was. I would start by setting a base point. That's going to be my point of reference. I'm going to put it on what you might call the equator there of the torus. And then I would describe the following two measurements. I would first talk about this angle T that says, okay, how much do I need to, by what angle from the center of the doughy part of the donut there, by what angle would I need to sort of rise, right? Measured at, positively as indicated there. And then from there, by what angle would I need to rotate around And I'll say specifically around the z-axis. Again, it's my coordinate system. I can define it however I want. And I'm going to view it like so, that I'm going to start from that base point. I'm going to rotate up by some amount t, and then I'm going to rotate around the z-axis by some amount s. I think it's a reasonable choice. What do you think? Right? Anybody got any better ideas for how to describe location on the torus? And I doubt you're going to beat this. You might come up with something just as good, arguably, right? But I think it's pretty streamlined. I think it's pretty natural. Obviously, there's kind of the circle, right, going around this way around the torus, and the angles are a great way to describe where you are in circles. And then also, if you were to make a slice, where the T is there, if you make a slice, well, then there's a kind of a circle going around the dough. In addition to those sort of circles going around the axis. I think this is very natural. So, notice, by the way, kind of like longitude and latitude, aren't they? So it's kind of a rip-off of an old idea. Okay, that said, once you have your coordinates identified, right? Once you have a coordinates system set up, all you got to do is write down a formula for position in terms of coordinates. Now, there's a little bit of geometry to be done here. There's in fact, a significant amount of geometry and a little bit of linear algebra. To write the coordinates of P. So let's see here. The first thing I would do is, keeping in mind we've got this starting point over here as our sort of base point from which we start. And I would say, okay, what happens if I rotate up by an angle t like so? And here's what happens. I pretty clearly am going to have that vector in orange plus, let's see if red shows up. This vector in red, and I'm going to leave the trig to y'all. This is a good little exercise in trig and three-dimensional geometry. If you know what that angle t is, and if you want to write down what that red vector is, that's the formula. So make sure you're good with sines and cosines, obviously, right? But you need to be able to interpret them in the context of that picture. Think about which coordinates of that red vector are which trig functions of that angle t, and just kind of think it through and write it down, and boom, that's what you get. Okay, details for y'all. Now that point P, of course, is not what I'm looking for, right? What I'm actually looking for is, I'm looking for x comma y comma z, right? I'm looking for my point R. And I also know that the way I turn P into R is by rotating. And here's another exercise left for y'all to read, but rotating around the z-axis. Right? That's a linear algebra problem. Y'all have all taken linear algebra, and I've talked about this a million times, right? That rotations are linear transformations. Linear transformations are matrices. Matrices are understood by their columns, and the columns are the images of the standard basis vectors. So you just have to think through, in this kind of a rotation where I rotate counterclockwise, as seen from above, around the z-axis by an angle s, what happens to the standard basis vectors? That gives you the columns. That gives you the matrix. So make sure you can do that. Again, come to office hours. I would love to help anyone who's maybe a little shaky. Maybe, it was a long time ago. I kind of forgot how that works. Come talk to me. I'll be very happy to help. Right? But I do need to make sure that everybody is good with being able to write down matrices describing, for example, rotations like this. And at this point, it's all over. It's all over but the shouting. Because we described, let's see if I can get this all on the page. We described how to find, what color did I use? Well, I started with dark blue as that point. I don't remember what color I used. I'm going to just use orange. We wrote down the P vector was that. And then we talked about how to do the rotation. The rotation is that. And orange, rotated by blue, gives you purple. And so you multiply this out. And again, that's matrix multiplication. You all know how to do that. Now, detailed devils, make sure you can do that, right? Boom, there's your formula. There's your parameterization. There is your parameterization of the torus. This is a really cool little technique. Again, let me just remind you, it's kind of a two-step process. Step one, choose, and I emphasize choose. This is up to you. You get to decide what your coordinate system is that you want to capitalize on here. Make a coordinate system, make it natural, right? Make it make sense with the surface. Make it convenient for the surface. And once you've got your coordinate system picked, step two is to just do the resulting geometry to figure out how to write position anywhere on the surface with coordinates s and t in terms of s and t. Again, sometimes there might be several steps in the geometry, and the geometry might even get a little hairy sometimes. That is what it is. That's the nature of the beast. Okay. Okay, moving along. Sometimes, actually, you know what? I'm going to zoom. There we go. A little bit more room to work. Sometimes what you want to parameterize is so close to something that you already have. And at that point, well, oh my gosh, why should I have to kind of reinvent the wheel? I mean, most of what I want is almost exactly what I already have. Wouldn't it be nice if there was a way to take an existing parameterization and just tweak it just a little bit? Just figure out how does it need to be tweaked, and then based on that tweak, parameterize a whole new surface. So that's what we're going to see here. I'm going to start with an existing parameterization. Let's think about the unit sphere. Now, y'all are accustomed to seeing the unit sphere described with a rectangular equation, but it sure is simple when you write it in spherical. So let's start with that. And once you have this very simple, by the way, graph, right? I have rho solved for as a really desirable function of phi and theta, constant no less. Once you have it written as a graph, you can write down the spherical graph parameterization, and bam, there is your parameterization of the unit sphere. Now, we just talked about that method just earlier today, so give yourself some time to digest that method and apply it in this circumstance and persuade yourself. Make sure you're comfortable that this is what you get out of this formula. And let me just remind you that what this gives you is rectangular position, right? So this is x, y, z as functions of phi and theta, and then you can observe that this vector equation can instead be written as three scalar equations, and you might call this the sort of the coordinate representation of that same parameterization. So take your pick as to how you write it. Same thing. These are really morally the exact same parameterization. It's just a question of how you write it down. Okay, so let's see here. Let me get my colors straight. I think I started in green. So for the unit, let me do it like this. For the unit sphere, and I'm going to go back to that equation, these are how I write that parameterization. So what if I want to parameterize this ellipsoid like so? Now that's not the sphere. It's not the unit sphere. But it's close. Oh my gosh, look at that equation. That equation's so similar looking to the equation of the sphere. It's something squared plus something squared plus something squared equals 1. Oh my god. It's so, and now, almost exactly the same thing. We already know from chapter 2 that it's mere little tweaks that allow me to turn the equation of a sphere into the equation of an ellipsoid, right? This is that deformations business that we talked about. So, and you can see it right here in the equation. Everywhere I have an x, I need to replace with x over a. Right? And we also know what that does geometrically. Geometrically, when you, in an equation, everywhere you see the x, you replace with x over a, we know that that stretches by a factor of a in the x direction. Right? So, this is not a huge tweak. And so the question is, can I take this knowledge of what happened in the equation and can I use that to tweak my existing parameterization? And yeah, absolutely. It's actually really easy to do. I mean, I already saw that just everywhere I see an x, I have to replace with x over a. Okay, how about I'll do that exactly right there. Right? The same thing that I did in the equations, do the exact same thing in the parameterization. And then, of course, now for this new parameterization, yeah, you'd probably want to go ahead and solve for x and by the way, analogously for y and z. So solve for x, solve for y, solve for z, and boom, parameterization. Okay. Now here's a different way to think about the same thing. It's a morally equivalent idea. I'm just going to come at it a little bit more geometrically, a little bit less symbolically. I know what this does, right? When I replace x with x over a, I know that all of my x coordinates are going to get a times as big. That was kind of the whole point of replacing x with x over a, is that it just requires those x coordinates to be a times as big in order for the algebra to still work out the same. So how am I going to make the x coordinate a times as big? I'm going to take the formula for the x coordinate and I'm going to multiply it by a, and guess what? That makes the resulting values of x a times as big, right? Not a deep suggestion. If you want to make the x coordinates a times as big, cool, go ahead. There it is. I multiplied them by a. All right. Again, likewise with the y and the z. So this too gives me a new parameterization. And at a glance, you might say, slow down there. Wait a second. How are those the same? Those don't look the same to me. They are, in fact, the same resulting parameterizations. Because keep in mind, when you write down your, r vector as your position vector, you're literally saying that you're writing down the coordinates of x, y, and z. And algebraic appeal... hang on a second. Algebraic appeal. Those really are the equivalent equations. It's the same thing, just whatever. I mean, it's a notational difference, I suppose. Certainly, if in the equations on the right, if you were to solve for x and y and z, like we noted, then of course you would get exactly what's on the left. So think about it geometrically, think about it algebraically, symbolically, take your pick, doesn't matter. You're going to get the same thing either way. Good technique though, that we started with a parameterization of a sphere, and by just a little tweak, not reinventing the wheel or anything, just a minor little tweak, now we have a parameterization of the ellipsoid. Is everybody on board? Is everybody following? Is everybody happy? Happy as you can be for math class on a Monday morning? Everybody's all right? Cool. Moving along. I've already talked through this point here. The book does give a bunch of examples. They're good examples. I hope you'll look at them. They are, however, about interpreting parameterizations, not creating parameterizations. Again, my experience... physics classes pretty similar to engineering classes in a lot of ways. I think you need to create, I'm going to say most of the time, right? So I think it's important to know how to create, not just how to interpret. Okay. All right, moving along. This next business, this is pretty straight up readable. I hope y'all will give this a look. I think the book's take on this is quite nice. I like it. very well. They create this idea of something called a coordinate curve, and it's basically just a kind of a rip-off, kind of a tweak of the idea of a parametric surface. It's the modest observation that if you have a function of two variables, and if you take one of those variables and fix it so that it is now no longer a variable, it's now a constant because you fixed it. Now, modest observation, you have position as a function of one variable, otherwise known as a curve. Right? Parametric curve, and we've studied parametric curves quite a bit. So anyway, I think it's a pretty straight read. Notice that, so this is just an example where I use phi and theta as my parameters instead of s and t, but that's just letters, right? It shouldn't be a big deal. I like this because it's geometrically relatable. We already have a good understanding of phi and theta on the sphere, so I think this makes it geometrically satisfying. And then a couple of little quickie observations about partial derivatives being velocities, and what we get, and here's where we're going to pick up, is that if you have a parametric surface, let's see here, okay, if you have a parametric surface, as a function of, let's say phi and theta, but whatever, any two parameters, right? And if you're interested in understanding the area of a little piece of surface in terms of the corresponding little piece of area in the phi theta plane, and if you want to understand the relationship, if you want to understand, okay, what happens when I plug into my parameterization, when I take all the points in that little green square. By the way, that green square, the area of that green square is pretty clear. It's d phi times d theta. It's right there looking at us, right? But if I want to use that to understand what the resulting area is on the right, on the surface, right? By how much does that phi theta area get kind of stretched out by the parameterization? Well, the way it gets stretched out is it gets turned into a little parallelogram. The edges of which I know, right? The edges here, you can just write down formulas for, and if you know those edges, then you can compute the area, and that's going to allow you to compute your stretching factor. And just like with curves, remember the big thing that we needed in order to use a parameterization, in order to pull back through the parameterization, the big mysterious thing that we needed was the stretching factor. Same deal here. We're going to compute the stretching factor. And that computation is really pretty straightforward. It's not that big a deal. Again, I already agreed that I know what these edge vectors are. Those edge vectors are that and that per the previous page. And again, make sure to read through those details. This area then, ds, well, I have a pretty standard formula for how to compute the area of a parallelogram in space whose edge vectors I know. It's the magnitude of the cross product. So, boom, there's that blue area right there. Chapter 1 formula. And if I want to relate that, though, to my input area, d phi d theta, notice that the d phi and the d theta, they just factor right out. Linear algebra and all that, right? Make sure you're clear on why they factor out. That's just a couple of facts from linear algebra. And so now, as desired, I have it written in, let's see here, I missed the thing again. Okay, I have the formula that tells me what is the factor. What is this multiplicative factor that I multiply by green area to get blue area? When it's staring right at me there, that multiplicative factor is that. This is what's left over. Okay, so this is a good general formula. And again, make sure to read those details. I think it's a healthy exercise. Let's see, I'm going to try to clean up there we go. And, missed it. Ooh, it's so hard to... Got it. Okay, so the factor that multiplies by green area to get blue area. New formula. Make sure to know this formula. It's the magnitude of the cross product of the partials of your parameterization. Okay, let me pause before I get to the next thing. I know I skipped some of the preliminaries, again, for y'all to read, right? But other than those preliminaries, everybody see how I used the geometry of that parallelogram? And boom, there's our stretching factor. Okay, now here's a little twist that we're going to put on it. This is largely a notation thing. This vector here, the cross product itself, ends up being important in a lot of ways. So that's what I'm going to give a name to. Right? That's what we're going to call capital N. So remember, the stretching factor is the magnitude of that capital N, right? It's not capital N itself. The stretching factor is the with the colors, hang on. The magnitude of that capital N is your stretching factor. So why are we interested in capital N by itself? Well, if you look back up here at this picture, and if you recall, let's see here, let me erase the distractions there. If you recall, these vectors are tangent vectors. That means that these partial derivatives are tangent vectors, and now geometric appeal, if you have two tangent vectors to a surface, and if you cross them, then the result is perpendicular to the surface, and that is my capital N. So it's kind of geometrically interesting then, right? N is not just, the thing whose magnitude is the stretching factor. It's also orthogonal to your surface always. And that's ends up being really useful. We're going to make big use of that later on in section 7.2 and 7.3. I think we're starting off with it in 7.2. Okay, so just notation. Now there's a related bit of terminology we need to talk about. Let's see here. Let me come down to here. Related little bit of terminology. What are we going to call this thing? It's a vector, right? Sure. It's a normal vector. We just discussed, right? It's always perpendicular to the surface. We need to call it something else. It's not just a normal vector. It's a special normal vector. It's a normal vector which you can remind yourself it comes right out of the parameterization. Remember, R, the thing that gives position R as a function of your parameters, that's the parameterization. And notice that that's where N comes from. N comes straight out of your parameterization. It is entirely dependent on your parameterization, how you chose to parameterize it. And remember, there's lots of ways to parameterize. It's not like there is only one single magic parameterization. There's loads of them, right? If you and I both parameterize the same surface, yeah, we probably will come up with different parameterizations, different formulas for R, and therefore we would have different capital N vectors. So, to emphasize that this is highly dependent on the parameterization, I like to call this the parameterized normal vector. I don't know, I find that satisfying. Now, for whatever it's worth, the book disagrees. The book calls it the standard normal vector. And I get where they're coming from, because this is a standard choice on how to write down a normal vector from a parameterization. The problem I have with this term is that if you're not thinking very, very, very carefully about this, you might think that this normal vector is somehow standard to the surface itself, and it's not. Very important. There's lots of parameterizations. They will all produce different ends. And I think it's weird to have a bunch of different things all called standard. Doesn't it? I don't know. Maybe that's just me, but I find that very uncomfortable. So anyway, heads up, the book's going to call it standard normal vector. I am going to call it the parametrized normal vector. Okay. All right, how are we doing? Pausing. Questions? Everybody's happy. Okay. All right, so we've got ourselves an area stretching factor. Now let's entertain the question of, let's suppose I wanted to compute the amount of area on some part of the sphere. So here's some kind of loosely triangular shape region of the sphere. How would I compute that area? Well, there would be some sort of corresponding shape like this, maybe. Something like that, I don't know, whatever. Back in the phi theta plane, and I would compute the area on the right by pulling back to the left, and all I have to do is insert my stretching factor, and boom, right? That allows us to compute the area. So we're going to actually execute that down here in this next example. I'm going to compute the area of the entire unit sphere. And side note, I know that you all already know the formula, right? It's written down in a geometry book somewhere. But again, any formula you find in a book, well, you're just trusting somebody. How do they know? Where did they get it from, right? So plus, again, reminder, I know y'all are sick and tired of hearing me say this, but it's not about the formulas, it's not about the answers, it's not about facts, right? It's about reasoning. What we are interested in math in general, really, is reasoning and how we draw conclusions and how we connect ideas and stuff like that. Okay, so anyway, here we go. Unit sphere. Here's the parameterization. The way I compute the stretching factor, well, apparently I'm going to have to compute the magnitude of n. N is a cross product of the partials, and the partials come out of the parameterization, right? So I'm going to have to first parameterize, second take the partials, third take the cross product, fourth compute the magnitude. It's a multi-step process, but that's just what it is. That's what the formula says that we've just derived. And okay, so there's the parameterization. There's the partials. Make sure you can do that. Significant, non-trivial little bit of derivatives of trig functions. And oh, don't forget that when you are taking a partial, the other variable is to be viewed as a constant. And it's very confusing, especially when your variables are phi and theta, because they look so much alike. And so I'm just telling you right again, this, my experience, it's so easy to be taking a partial with respect to theta and forget that means phi is a constant and accidentally take a derivative with respect to phi. Easy to mess that up. So make sure you can do that. Then we take the cross product. And once you take the cross product, you've got to compute the magnitude. And this is all healthy algebra. This is all stuff that everyone should do once in their lives. I've done mine. It's your turn. Please do check through all this algebra. Make sure you can do it, and make sure you believe it. And by the way, there's some particularly subtle and important and ultimately very useful in your futures algebra in that very last step. Looking at the magnitude of this cross product, there are, if I remember correctly, 3 instances in that one calculation. 3 instances of the Pythagorean identity coming up and being indispensably valuable in simplifying it. And it's kind of amazing at a glance. When you look at that nasty formula for that capital N vector, that's a nasty looking formula. How could the magnitude be just sine phi? Seems a little too good to be true. But it really is that simple. Very nice. Okay. All right. Let's see here. So, we're almost done. Let's just go ahead and spike the football here. We just computed our stretching factor. And stretching factor is how I take input area and turn it into output area. And now all I have to do is just add up over, let's remind ourselves we're looking at the entire unit sphere. The entire unit, I can fit this all on. The entire unit sphere is obtained by letting theta go all the way around and phi go from 0 to pi. And you plug and chug that integral. And we get the familiar formula that we all memorized back in high school geometry class. The unit sphere has area 4 pi. This is a good spot to end it. We'll draw the line here. You all have a good rest of your Monday and see you Wednesday.